Welcome to Chapter 7.1, Apply the Pythagorean Theorem. Now, Chapter 7 is all about right triangles and what is known as trigonometry. Now, trigonometry is a branch of geometry that relates specifically to right triangles. So this whole chapter, right triangles and trigonometry, don't be worried about the word trigonometry, just means basically geometry dealing with right triangles. So again, Pythagorean theorem we talked about a little bit earlier this year comes from Greek mathematician Pythagoras, and it is related specifically to right triangles. Does not work with other types of triangles, only with right triangles. So what Pythagoras' theorem originally was based around was the idea of hypotenuses and legs. So in a right triangle, the side opposite the right angle, or across from the right angle, is always known as the hypotenuse. The other two sides, which are adjacent to the right angle, so the two sides that meet at 90 degrees, are known as the legs. Typically, we'll call them leg 1 and leg 2. So just doesn't matter, they're interchangeable, but the two sides that meet at 90 degrees are the legs. The longest side of your right triangle, which is the side opposite the 90 degrees, always the longest side of the right triangle, is the hypotenuse. So our first theorem that we're looking at, obviously, is the Pythagorean theorem. So what Pythagoras' theorem originally stated was that if you take the two legs of the triangle and you square each of them and add them together, that equals the length of your hypotenuse squared. Now, we've modernized that to kind of the definition you see here that says, in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of its legs. So we can look at that kind of like this equation right here. Leg 1 to the second power plus leg 2 to the second power equals the hypotenuse to the second power. Or what we typically call that is a squared plus b squared equals c squared. What you want to keep in mind is the hypotenuse is always the letter c. So in these Pythagorean equations that we'll be looking at, the hypotenuse, the side opposite the 90 degrees, is always the letter c in your equation. And then A and B are always the legs. Doesn't matter which leg you make A or which leg you make B. So for the examples, for example 1, asks us to find x using the Pythagorean theorem. Write your answer in simplest radical form. So we'll come back to that idea of simplest radical form when we get there. But the first thing to keep in mind as you're working with Pythagorean theorem problems is you would want access to a calculator. Now, if you don't have a calculator at home, easy thing is on your Chromebooks, just obviously go to Google, type in calculator or scientific calculator, and one pops right up. So as we look at these, finding x using the Pythagorean theorem. So in example A, they gave us the sides 8, 6, and x being the hypotenuse. 8 and 6 are the two legs. So my setup would be 6 squared plus 8 squared equals x squared. 6 squared is 36, 8 squared is 64 equals x squared. 36 plus 64 is 100 equals x squared. And then to solve for x, to get rid of the squared, we would have to do the square root of both sides. So x would equal 10. In B, we have the hypotenuse and a leg. We are trying to solve for the missing leg. So our setup for B would be taking our two sides squared, so x squared plus 3 squared, equals our hypotenuse, 5 squared. So the next step in our equation, x squared plus 9 equals 25. Then what we'd want to do is start to solve for x. So subtract 9 from each side. X squared equals 16. Square root of both sides, and the square root of 16 is 4. Then in C, and this is where that idea of simplest radical form comes in. If they want the answer in simplest radical form, that means they want you to simplify it without decimals. So don't just type the square root into your calculator and put the answer as a decimal. Most of the time, it's okay to use a decimal answer unless the directions specifically say simplest radical form. So in order to do that, we'll come to that step after we solve for x. So our initial setup is 4 squared plus 6 squared equals x squared. So 16 plus 36 equals x squared. 52 equals x squared. So x would be the square root of 52. Now this is where we need to see if we can simplify the square root of 52. So what we want to do is check to simplify what's inside the radical. So what we want to think about, are there any perfect squares that can be divided out of 52? So a perfect square, again, is a number like 4. The square root of 4 is 2. Or 9, 16, 25, 36, 49, and so on. So perfect squares are numbers where we can take the square root and not get a decimal. So in this case, 52 divided by 4 is 13. So I can split the square root of 52 into the square root of 4 times the square root of 13. Then the square root of 4 is 2. So my simplified radical form of the square root of 52 would be 2 times the square root of 13. And that should be a review of Algebra 1. If you do need some help on simplifying radicals as you are working on the practice problems, let me know and I can get you some examples. Example 2 is a typical story problem based around a ladder. So in this case, we were told a 16-foot ladder rests against the side of a house. Base of the ladder is 4 feet away. Approximately how high above the ground is the top of the ladder? So we have a diagram here to the right, gives us the 3 parts, 16 feet being the side of our ladder, 4 feet for how far it is away from the house, and our height along the house being x. So using Pythagorean theorem, 4 squared plus x squared equals 16 squared. Then we'd have 16 plus x squared equals 256. Subtract 16 from each side, and x squared equals 240. Then the square root of both sides, and x would be the square root of 240, which is approximately 15.49. So our multiple choice options, the closest would be 15.5 feet. So example 3, again, is another word problem related to the ladder. In this case, they did not provide the drawing, so the first thing that I did once after reading the problem was to draw the triangle that you see here. So in this word problem, we know the ladder rests against a wall 23 feet above the ground. So I know my side of the triangle going directly up is 23 feet. The base of the ladder is 6 feet away from the wall, so those two sides meet at the right angle, so they're my two legs, 23 feet and 6 feet. We are solving for the length of the ladder, which in this case is our hypotenuse, so x feet. So in our setup, 23 squared plus 6 squared equals x squared. 23 squared, 529, plus 36 equals x squared, which is the square root then of 565. Square root of 565 is approximately 23.77. So because they didn't say put the answer in simplified radical form, I would just put into your calculator square root of 565, and again, round your decimal typically to 2 decimal places unless directions tell you otherwise. So 23.77 feet long. And then our last few examples here. Example 4 asks us to find the area of an isosceles triangle with side lengths of 10 meters, 13 meters, and 13 meters. So again, I just began with drawing myself that image of 10 meters, and then I knew my 2 congruent sides of 13 and 13. Now, in this case, what you want to keep in mind is the area of a triangle is always 1/2 the base times the height. Base and height are the 2 parts that meet at 90 degrees. So if we look at an isosceles triangle, we do not have a 90-degree angle, so we need to create one. So what you want to think about is you would have to draw in your altitude or your height, in this case right here, the purple segment. So that is what would be x. So in order to find the area, we first need to find the height of the triangle or the altitude, which is x. So when we split that always will split the bottom or our base in half. So half of 10 gives us this part of 5 meters. So the triangle that's created, we still have the side of 13 meters, but the 10 down here on the base becomes 5 meters, and then our other leg is that height. So we just took the triangle from over here, and this is our half section that we created. So then we use the Pythagorean theorem to find x. So 5 squared plus x squared equals 13 squared. 25 plus x squared is 169. Subtract 25 and square root it, giving us x equals 12 meters. Then once we've found x, we can plug that in with our base to figure out our area. So we have to use that original base of 10 meters times our height of 12 meters and then half. So half of 10 times 12 would give us an area of 60 meters squared. So example 5, we have A and B here, is that same concept. We first need to find x, which would be the height of the triangle, and then we would use the area formula to solve the problem. So in these problems, we are always given isosceles triangles, meaning 2 sides of the bigger triangles are congruent. So in this one, 18 and 18 are our isosceles sides. 30 would be my base, and I need to find x here for my height. So when I split it, 30 split in half gives me 15. So my setup would be x squared plus 15 squared equals 18 squared. Then when we get to solving for x squared equals 99. The square root of 99 is approximately 9.95. So our area formula, 1/2 of 9.95 times 30, gives us an area of approximately 149.25 feet squared. And then for B, again, even though they turn the triangle sideways, base and height always meet at 90 degrees. So our base would be this part here of 20 meters. So in this case, we would split our 20 meters in half, giving us 10 and 10. So our setup to find x would be x squared plus 10 squared equals the hypotenuse of 26 squared. X squared plus 100 equals 676. X squared is 576. The square root of 576 is 24. So to get our area, then we're back to the original base times our height of x. So 20 times 24, and half of that would give us an area of 240 meters squared. So the last idea that we need to cover today is not an example, but just a table here, and the idea of Pythagorean triples. So Pythagorean triples are three numbers that if you have these three sides on any triangle, you know that you have a right triangle. So if you ever look at a triangle and you're just given side lengths, Pythagorean triples always create right triangles. So if we ever have a triangle where the sides are 3, 4, 5, we have a right triangle. 5, 12, 13, 8, 15, 17, or 7, 24, 25. Those four across the top are your four most common groups of Pythagorean triples. Then, as you look down the table, those are just multiples of these originals. So any of these combinations that you see in this table always guarantee a right triangle.